So we know what the expected value of a random variable is, at least if the random variable is discrete or continuous. If x is a discrete random variable, then the expected value of x is defined as the sum over all values in the range of x, 1 to n, xi times the probability mass function f of xi, where n is infinity if the range is countably infinite. If the random variable is continuous, then we define the expected value of x as the number integral minus infinity to infinity x times the PDF f of x dx. We also know what we mean by a function of a random variable. So if x is a random variable and g is an arbitrary function from r to r, then y will be a new random variable defined as the composition of g and x. So in this lecture, we are going to put these two things together and figure out the expected value of y, the expected value of a function of a random variable. If x is a discrete random variable, then the result is as follows. The expected value of y is then equal to this same sum, but we sum g of xi times f of xi. Compare that to the expected value of x, where we just sum xi times f of xi. I'm not going to prove this, but we can at least lend some credibility to this formula. So let's say that we have this following example. I have the probability mass function of x is 2/3 for x equal to 1, 2/3 probability that x will end up with 1, 1/3 for x equal to 2. For this random variable, the expected value of x is the sum over these two terms. So it's 1 times 2/3 xi times f of xi plus 2 times 1/3. The value it takes multiplied by its probability, and we do it as a sum over all possible values. So let's define a new random variable y as x squared plus 1. Then the probability mass function of y will then simply be, well, when x is 1, y will be equal to 2, and the probability for that will be the same, 2/3. Whenever x is 1, y will become 2. Whenever x is 2, y will become 5. So 1/3 probability of this. So the expected value of y is then, well, 2 times 2/3 plus 5, which is the second possible value, times 1/3. And you can see what's happening here. Here we do x1 times f of x1 plus x2 times f of x2. Here we need to plug this x1 into the g function first. So this becomes g of x1, which is 2, times f of x1 plus g of x2 times f of x2. So this is the basic reason behind the formula for the expected value of a function of a discrete random variable. The corresponding formula for a continuous random variable is pretty similar. We just need to change sums to integrals. So if x is now a continuous random variable with PDF f and y is some function of x, then the expected value of y will become this integral, or we do g of x times f of x. Compare that to the expected value of x, which is minus infinity to infinity. Well, then we just do x times f of x dx. For a function of x, we need to do g of x times f of x. This result is hugely important in probability theory. It is still true that the expected value of y is the integral from minus infinity to infinity y times the PDF of y dy. I put the y here just to remind myself that it's now the PDF of y. That is certainly still true. The big advantage with this formula is that I don't have to find the PDF of y. And in many cases, that's a pretty difficult problem. So it's just a really nice shortcut finding the expected value of a function of a random variable without finding the distribution of that function of the random variable. Here's a simple example. Let's say I have a random variable x with range 0 to 1, and the PDF of x is x2 to the 3. I'm not interested in the expected value of x, I'm interested in the expected value of y, where y is square root of x. So my f of x function is x2 over 3, and my g of x function is square root of x. According to the formula, the expected value of y is then, I'm supposed to integrate from x from minus infinity to infinity, but since f of x is 0 outside 0, 1, I can just do the integral from 0 to 1. G of x square root of x times f of x, x2 to the 3 dx. So you can calculate this integral however you like, maybe by hand, or I'm using Maple here, integral 0, 1, g of x, f of x, and it comes out to 2 over 21, which is the expected value of y.